All right. So before we get started, I think I okay. So my goal today is to convince you that the material that we are gonna look at in this part of the course is important and useful. Okay. So I'll start with some demos so that you will feel a little bit more likely to pay attention, and you start to believe me that by putting effort into learning this stuff, it will be useful for you in your career, probably. Okay? Okay, so bad thing is that my notebook keyboard is like on and off, so I need to use this stupid one, so it'll be pretty clunky at times. Okay, alright. Okay, so in the second part of this course, there will be two main topics that we will look at. Okay, the first part is linear algebra. So what exactly are linear algebra? So linear algebra consists of many small interconnected topics, but basically you can think of it as two topics basically. So one is really about matrices. So you have a matrices and you want to do something with it, okay? Like you write a set of linear equations and then you try to solve it, okay? And when can you solve it? When there are no solutions, when there are more than one solutions, how can we tell them apart? So this will be like the first part of linear algebra, okay? So matrix and solving equations. Okay, I'll give you the handout, so you don't have to take notes. Just try to think along. Okay, it will be more useful if you try to think along while we are talking about stuff. Okay, if you don't follow, please interrupt me. Okay, I'll try to go slow first. Okay. So the first part is like when you do anything related to machine learning, data science, like it will be mostly on related to this aspect of linear algebra. Okay, because all the inputs that we put into the many machine learning algorithms, they come as vectors. Okay, an image is a vector. Okay, a sample point is a vector. Okay, if you use ChatGPT, right? You know how the text that you type get fed into the LLM. Okay, we'll look at it today, so I'll give you some demos. Okay, we'll try to, if we have time, we'll try to train our small little language model so that you learn about stuff and you see the connection between what we've done today, or not today, like what we've done in class with the stuff that you're using. Okay. All right. So, but the other part of linear algebra is about something called vector space. Vector. This is more abstract. Okay? Like the property of vector spaces. There are many related definitions like span, linear combinations. These are stuff that I'll try to you practice a lot of it, so then you try to get the idea, but it is more abstract. But everything relies on like these facts that we prove in this aspect of linear algebra. So there will be a bunch of definition like span, linear combination. We'll look at some of them today. Independence, dimension, basis. So these are this will look abstract at first, and after we're done with the course, it might remain abstract. But I hope you can grab some of the ideas. Okay. All right. Okay. So enough for the chit chatting. Okay. So let me show you with some cat pictures. Okay. So this is a cat. Okay. Okay. So you can think of this as for each pixel. Okay. Each pixel is a number from 0 to 255. I think. If the number is high, then it's white. Okay. If the number is low, like 10, 0, these are like dark pixels. Okay. So how many pixels do we have here? So it's about 1,000 times 800 or something. Okay. You can think of this as like a million pixels, I guess, roughly a million pixels. Okay. So if you want to keep this image in your memory, you probably need like a million numbers, okay, to get this cat. Okay. But my question is, think of this as an information. Okay. So you have a cat pictures. Currently, to keep the full, like the whole pictures accurately, you need a million numbers. Okay. But do all pixels important? Do they have the same importance to the to how the image would look? You can see here, like this part of the image is like pretty blurry, right? So it doesn't hurt to make some errors here. You don't really need like this to look like exactly like this. You can have another image with different value on this part, and you still recognize it as the same pictures. Okay. Okay. My question is, think of this as compression. Okay. Like when I was young, the internet was really slow. You might not be born at the time when the internet was slow, but when you watch Netflix on the low speed internet, do you see the image will look like blobs, right? You can see a lot of boxes, right? Okay, so that's how the image compression works. It tries to capture most of the important aspect of the frame, and then we'll do that too. Okay, so what I will show you now is some trick that would allow us to only keep maybe 10% of the numbers and still recover like pretty much the same image. I hope. Okay. Okay. The way we do that is this. So let's start by asking a question, okay? Like, do each, so we can look at this image as a matrix, okay? A matrix has many rows and many columns. This image has like 800 or maybe 750 rows and about 1,000 columns, okay? So what if I want to keep only one row of this image? Or in other words, I would like to ensure that every row are the same. So what does the image would look like? If I only keep the first row, it will look like this. So if you look at the image, okay, and if you look at the first row, maybe it will look like some dark points here, some lights point here. But if you only keep one row, like So the image will look like there will be strips, right? Because all the rows are the same, okay? And it doesn't look like an image, okay? So that's an image with one row, okay? However, I would like to keep some other things, okay? What I would do is like, I would keep the first row, or I would keep one row, okay? And all the other rows will be a scaling of the first row. What I mean by scaling is that maybe so let's make sure it's readable, okay? So suppose let's try this. So suppose my first row look like this. Let's make sure it's just black and white, okay? So if my first row look like this, and then if I keep exactly the same row as the first row, I would see something like pattern that look like this. No, see, it's just a strip, okay? But if I don't keep exactly the same value, but I keep the same first row but with different intensity, okay? So I can make the whole, so the row would look like this, but each row would have some, might be lighter or darker, but I do that proportionally for the entire row, okay? What does it look like? So let me show you what it look like. So let me run some of my code. So this is my cat. Does it look like a cat? It looks like a cat in Roblox, probably. I really hate Roblox. I mean, the wolf are really, it kills me every time. I can only kill the rabbits. And I only stay only 2 nights and I die. Very stupid games. And I spend like hours and hours. Okay, so this is my cat. Does it look like my cat? Okay, but you can see there's something that looks like a strip. Okay, so every row follow the same pattern, but with some different intensity. Okay, but they follow the same patterns. Okay, so this is what I'm talking about. Okay, I have the first row. Okay, and every other row is just a scaling of the first row. So if I take the pixel from the first row, maybe the second row is like the first row times 0.9. So it's a little bit darker. Maybe the third row is the first row times 1.5. So it's a little bit lighter. But they all follow the same strip patterns. Okay. Okay. This is an image that look like nothing. Okay, look like nothing. But this kind of image, I can represent this image that contains a million pixels using just roughly maybe 2,000 numbers. Okay, 2,000 numbers. So it's like 2%. Okay. The way I do it is that I keep the first line. Okay, I keep the first line, and then the other line is just the scaling of the first line. So I keep the first line, and for each other lines, I only keep the one number. Okay, let's say it's like, okay, this is the first line times 0. This is the first line times 0.1, stuff like that. Okay, so I only keep the numbers that I keep is like the number of columns plus the number of rows. Okay. If you think of this, the whole image contains the number of, also let's say, let's put in some numbers. Okay, so suppose I have m rows and n columns. Okay, instead of having to keep m times n numbers, I only keep m plus n numbers. Okay, so you change from the product to the summation. Okay, but it doesn't look like a cat, right? It doesn't look like a cat. No. Okay, so let me instead of doing that, let me keep another row. Okay, so let's say if I have more flexibility, so let's say I keep 2 rows. The image look like this. Wow, does it look like a cat yet? No? Okay, sorry about that. So let's try 3 rows. Let's see when my cat would appear. Does it look like a cat? Do you see that it look like something? It's becoming a Roblox cat. Let's do 5. So about 10, if you have about 10, you should see a cat. Okay? So I keep roughly 10 rows. Okay? 10 rows and 10 columns. And I have something that looks like my cat. Not really. So let's do it. Let's do 30. 30 should be enough, I think. Yeah? Looks like a cat now. Okay? So let's see how much, how many information that we keep. We keep basically 30 rows, right? So if you look at these pictures, so we basically take the first few rows like this, okay? But not exactly the first row, but we keep the information like this much for each row, okay? And we keep 30 columns, okay? And then we roughly have the cat back, okay? The cat back. Okay, so what does this mean? Okay, so instead of a million, so let's say I have a million numbers. With this technique, okay, I only need roughly maybe this. So for each row, I keep 2,000 numbers, and I have 30 rows, right? So it basically 6%. Okay, so I only need 6% of the numbers, and I have roughly. It might not look exactly like my cat, but it's close enough. Okay, you can also do better if you do like 30, 50. Okay, so this I think this is good enough. But you can see that some of the fur, like there are many parts of the image with high frequency, like the cat's nose, this fur that got distorted. But I think this looks good enough. Okay, and this is like when you watch Netflix on slow internet, you see a box like this, right? It's the same kind of, data compression. Okay, it uses linear algebra. Okay. So let me show you a little bit like what we did here. It's exactly so instead of having this matrix this way, okay, we express this matrix as a multiplication of 2 matrices, smaller matrices. So this image is like, okay, so let me show you. So this matrix, the input, the starting image look like this, right? With 700 rows and this many columns. But instead of doing that, okay, I would keep this. I would represent them as a matrix with 700 rows of 30 columns multiplied with another matrix with 30 rows, 1,000 columns. Okay. So instead of having this big matrix, I represent them as two matrices, a product of two matrices, which are much smaller. Okay. Okay. So the reason why we're doing this is that we would like to reduce the amount of maybe memories that we are required when we wanted to submit the image. We want to transfer the image, right? So that's the old application of this technique. Okay. The modern application of this technique. Have you tried any image generation AI? เคยใช้ไหมครับพวกอะไรนะ stable diffusion stuff like that. Okay. You can fine tune it. You can fine tune it with your image, right? Okay. There's a technique called low rank approximation LoRa. Okay. If you use that, it will train much faster. It's basically this. Okay. When you have a big like inside machine learning models, it's entirely a bunch of matrices, and you do a lot of matrix multiplications there. Okay. And if you need to, sometimes you need to keep all the data as the whole matrix like this. Okay. But sometimes it's not. The important part of the matrix, of the weights, of the machine learning models is not that complicated. It's like our cat pictures. Not every numbers are important, okay? But you can somehow squeeze them and only represent the whole thing as a multiplication of smaller matrices, okay? And in this case, like if you have smaller matrices, you have smaller number of parameters. Then your optimization will run much faster because you have smaller number of things that you need to concern. Okay, so you may have a really big machine learning models, and when you wanna fine tune it, the part that you would like to update the matrices will not contain like a lot of data. So you represent them as the multiplication of smaller matrices, and then you can train much faster. So this is called LoRa, I think. LoRa. Like low rank approximation. So this is like low rank approximation. What I mean by low rank, what I mean by rank? Rank is the property of this matrix, or this the result of this matrix. Like in this image, we use 30. So this is like roughly the rank that we are talking about. So if your image is really complex, you have higher rank, so you need more rows. But if your image is like not that complicated, you can have low rank. So for example, like rank 1 matrix would look like this. You can guess the first matrix that we looked at. This is like rank 1 matrix. That it doesn't look like much, right? Doesn't contain a lot of information. But if you add more ranks to it, it can get more complicated. Okay. So we will learn about this later on, but I would like to show you cat pictures so that next time I talk about linear algebra, you feel like okay, little kitten, stuff like that. Okay. So all right, first part. Okay. Cat. Okay. We'll come back with this SVD thing and this matrix you can see what I did here. So let me show you the code. So I basically run one command, basically SVD. So I take the matrix and I put it into this singular value decomposition. It returns me three things. Basically, turn me two matrices. And then when I reconstruct the matrix, I just take the first k columns. K is the rank, like 35 or something. So I use 5 here. So I take the first 5 columns and multiply by basically the first 5 rows, and I get this, stupid cat. Okay, I get this robot cat. If you play Roblox, you can add me as friend and give me stuff like your fruit in your gardens. I am really poor. I only have like $1 million. Not million Robux, million something in the garden that cannot buy anything. I also have a cat who doesn't do anything. I don't know why I have it. Okay. All right. So, okay, this is the first thing that we show you. Okay. Next, let's do something